In this last example, we are going to find a long-term behavior, and from this also the horizontal or slant asymptote of two rational functions. We're not going to graph the entire rational functions. We're just going to try to find what happens in the long run. So we're going to start with A, which is a ratio of two quadratics. Okay, so notice how they have the same power here. So here, I want to show you a technique for doing this. Okay, when you have ratios of polynomials that involve just looking at the leading terms for each polynomial that you have in the numerator and denominator. This is again because when x is really large, imagine x is a million, x squared, so a million squared will be a lot larger than maybe just x, which would be just a million. Okay, so the leading term is going to be way larger than any of the other terms, and it's going to dominate completely the expression when x becomes large. So y is going to be when x is large. Okay, so this is when x tends to plus or minus infinity. Y will be almost minus 3x squared over 2x squared. Okay, and if you simplify this, now they have like common powers of x squared, so it comes down to minus 3/2. So that means that what happens here is that we've got a function, okay, which approaches values of minus 3/2 in the long run. So what I don't get from my analysis is whether the function goes towards this horizontal asymptote from below or above, but it's going to go towards it. Okay, so so that tells me that y equals minus 3/2 is a horizontal asymptote. So y equals minus 3/2 is a horizontal asymptote. So in B, if I can try to do the same thing, when x goes to plus or minus infinity, y is going to be almost the same as minus 4x squared over 2x. Okay, now in that case, this simplifies to minus 2x. From this, I can only recover the behavior whether it goes to infinity or minus infinity. I cannot recover the asymptote entirely. So when the answer is not a constant, you have to do your long division in order to find if there's a slant asymptote. So here the y equals minus 2x is not, we'll see, is not the slant asymptote for that function. But from this we can actually recover if y goes to plus or minus infinity as x goes to plus or minus infinity. So when x goes to infinity, we can see that the behavior of y, which is minus 2x, well, if x is large and positive, y is going to be large and negative. When x goes to minus infinity, y is not going to be going towards plus infinity. I didn't want to write equal. I wanted to write tends to. Okay, but since there's not a constant here, I'm going to do long division to find what my slant asymptote is. So I'm going to take minus 4x squared plus 4x minus 1 and divided by 2x minus 7. Okay, so 2x, I need to multiply it by minus 2x to get minus 4x squared. So that gives me minus 4x squared after multiplying, plus 14x. And then we subtract. 4 minus 14 is minus 10x. How do we fit 2x into minus 10x? We need to multiply it by minus 5. So that's going to give us minus 10x. And now I'm going to need to bring down that minus 1. And minus 7 times minus 5 plus 35. I subtract, I get minus 36. So overall, my function y is minus 2x plus 5 minus 36 over 2x minus 7. So my slant asymptote is this part. This is the part that's That's not, so the minus 2x plus 5 is not the part that's going towards 0. This part will become very small when x is large, due to the fact that in the numerator I've got a constant 36, and the denominator I'm going to have numbers 2x minus 5. That's going to be really large if x is, let's say, 1,000,000 or minus 1,000,000. So my slant asymptote, as you can see, it was not minus 2x. Minus 2x just actually the part, the term that actually multiplies x with the slope of the asymptote. So I actually knew that minus 2 was the slope of the slant asymptote, just didn't know what the y-intercept would be. So the slant asymptote here is minus 2x plus 5.